Hello class, today we're going to dive into the general characteristics of gases as compared to other states of matter. We are also going to look at different ways we can measure pressure and the relationships between pressure, volume, temperature, and quantity of gas. This first plate posit aligns well with quest gases. The quest for gases, there's only one quest, so just keep in mind that some of the problems are from here, some of them will be based on the next plate posit, and even some questions from the last plate posit. Okay. So first, kinetic molecular theory of gases. This should be a review from honors. All particles are in constant random motion. We know that all collisions between particles are perfectly elastic, or like billiard balls. We make the assumption that they just bounce off each other and they keep moving. The volume of the particles in a gas is negligible. Well, we know that atoms take up space and that gas particles take up space. We make the assumption that the amount of space a particle takes up an individual particle is so very, 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 very tiny that it actually does not affect our overall volume. Whereas when we have a solid or a liquid, we know that that mass, that volume of that thing is very quantifiable. So we're going to assume that the volume of the particles in a gas is negligible here. We also know that the average kinetic energy of the molecules is its Kelvin temperature. So that means every temperature you see has to be converted to Kelvin. If you forgot about your conversion between Celsius and Kelvin, I hope not, but at this point, let's review. Celsius plus 273 gives you the Kelvin temperature. I know technically it's 273.15, but if you just use 273, you should be good to go. Some caveats here. We know this neglects any intermolecular forces that may be at play. We'll talk about that in the last play posit and what those things are and how they can affect gases. We're going to talk. The other thing we know is that the gases expand to fill their container, whereas solids and liquids do not. We also know that gases are compressible, and solids and liquids are not. So when we're looking at the different relationships, we're going to keep in mind that out of the 4 different variables of pressure, volume, moles, and temperature, whenever we're looking at 2 particular variables, the other 2 are going to be held constant. So here, when we're looking at the pressure and volume relationship, we know that as you increase the volume, the pressure goes down. Gases have more space to spread out. We also know that the converse is true. As you decrease a volume, the pressure increases because there's less space for the particles to move. So this is an inverse relationship. This is the only inverse relationship among the 4 quantities, which makes it really easy to remember for all the other ones. The other ones are all a direct relationship. So as we see here, when temperature goes up, the volume goes up. We know that we can increase our temperature, give it more speed, and as they have more speed, they like to spread out because there's a temporary increase in pressure, and to relieve that pressure, the only thing we can do is increase the volume. Here's my particles. Let's see, here's a gas. As I cool it down, they start to all slow down, and a lot of them tend to congregate towards the bottom because they're moving less, and we get back into our liquid or solid state. Whereas when I increase the temperature, we can see that they're colliding more, they're starting to move a bit faster, they're hitting the walls a bit faster, or not faster, but a bit more frequently. And eventually, if we really wanted to crank this temperature up, they'd be moving very, very fast, and a lot of collisions would be happening. This one's good. With the phase changes, you can actually see the phase changes here with pressure. So if I increase my temperature, it's going to take quite a bit, but as I increase my temperature, pressure starts to increase as well, and then as they start to spread out, pressure keeps going up, up, and up. And then I could even change my volume of my container here. And as I move this down, pressure keeps going higher, 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 more collisions. And it just keeps going. And I can move it even closer, and eventually I'm going to break my container because there's just too many collisions for it to handle. And ooh, here we go. This is about the breaking point. Boom. Oh, almost an overload. 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 Boom. And it breaks. It's fun. Go play with it. Anyway. All right. Need my calculator there. So we know that that is in a direct relationship with the temperature and volume. We also know the same thing with temperature and pressure. If you increase the temperature, we have more collisions, therefore we're going to have more pressure. Right? Same thing if you decrease, go the opposite way, it's still a direct relationship. Moles. If we increase the amount of moles of gas, simply put, if you put more stuff in there, you're going to increase the likelihood for collisions, and therefore we're going to increase our pressure. That makes sense. And we also know that we have a direct relationship with moles and volume as well. The more stuff we put in there, the more space it'll take up. This is based off of Avogadro's Law. We'll see this one fairly shortly. Okay. So a couple things we need to know. Our unit of temperature, we're going to be using Kelvin here. STP, we'll review that shortly, but that is when we are at 273 Kelvin and 1 atmosphere. 0 degrees Celsius is equal to 273 Kelvin. We label, we know N is equal to moles. Pascal is a unit of pressure. We'll talk about pascals in a minute. We know a liter is equal to 1,000 milliliters. It's also our unit of volume. And then the last thing, this is not a very common one we see, but it is useful information. 1 centimeter cubed is the same as 1 milliliter. You might see some volumes put in centimeters cubed, and if you know that conversion, that could be very helpful. Some useful pressure conversions for you as well. We have 5 different units we're going to look at. We have 1 atmosphere. That is ATM, that is our standard. We have 760 millimeters of mercury. This is also equal to 760 torr. They are interchangeable. As you can see, the numbers are the same. So if you see torr in millimeters of mercury, same thing. We also have kilopascals, kPa, and the counterpart is a pascal. While I don't think you'll see a ton of problems using inches of mercury, it is good to know that an inch is equal to 2.54 centimeters, which is then 25.4 millimeters, which means you can convert between millimeters of mercury and inches of mercury. Really, inches of mercury is useful for when you're looking at the weather. If you've ever noticed, the barometric pressure that they put on there is right here in inches. It is 30.19 inches. That's our atmospheric pressure right now. So since that is our atmospheric pressure, we could actually do that conversion real quick. We know that 30.19 inches of mercury, if we multiply that by 2.54 centimeters, and then times 10, because we know there's 10 millimeters in a centimeter, we get 766 millimeters of mercury. And if we divide that to figure out how many atmospheres it is, we're at about 1.01 atmospheres right now, which is normal. See, it is standard pressure. So when I say atmospheric pressure, that's where it comes from. Okay, so now it's time to look at our formulas. I've got a couple of different formulas here, and there's actually one missing. That's Avogadro's Law. We'll talk about that one in a second. Boyle's Law, we've talked about P1V1 equals P2V2. That's the only inverse relationship. Everything else is direct. We know that V1 over T1 equals V2 over T2. P1 over T1 equals P2 over T2. And then the combined gas law, which is a combination of all of them. Now with the combined gas law, if you know the combined gas law, it's really easy to figure out your simple gas laws. Say you wanted to know what okay, Lussig's law is? Well, I know pressure and temperature is applicable there, so I can just cross out my volume and look at that. It's the same relationship. You can also do that if you're looking at Boyle's law. You know that temperature is held constant. So you've got P1 V1 equals P2 V2 on the top. And you can do the same thing with Charles' law. You know pressure is held constant there, and you've got volume over temperature. So combined gas law is probably the most useful one we're going to use today. We'll get to the ideal gas law in a later play posit. Now we also have the same relationship for Avogadro's law. So Avogadro's law, sometimes called a Montan's law, I think. But that's pretty much the same thing. We know it's a direct relationship. V1 over N1 is equal to V2 over N2. N being your number of moles. So you can solve for the moles. And actually, I think we have a problem like that later on in this play posit. All right, so pressure of a gas is measured at 49 torr. We want to represent this in atmospheres and pascals. So let's do a simple conversion. All right, now if you set up your dimensional analysis right, we can actually do this in one nice step. So I know that I've got 760 torr for every 1 atmosphere. Okay, I'm only actually going to do the calculation twice, and then, or once rather, and then I'll just stop at each point. So I always put the unit I want to cancel on the bottom. If I set it up this way, torr will cancel. And I also can use that same relationship and do kind of a 2-step conversion there. I don't have to do it this way. 101.325 Pascal, I'm sorry. I don't have to do it this way, but I'm doing it this way just to show that you can convert between multiple units at the same time. If I did it this way, atmospheres would cancel, and then I would be in Pascal. So I can do this times the top, which is 1, divided by the bottom, which is 760. I know that in terms of atmospheres, if I stop right there, I'm at 0.064 atmospheres, if I talk about sig figs, so ATM. And then if I multiply that times 101.325, I will be in my pascals, which is 6532 pascals, which if we're talking sig figs, it's about 2 sig figs here, right? So 6,500 Pascal. So reading a manometer is something that is very useful, especially for lab questions. There's a chance that you could be asked a multiple choice or a lab question dealing with how to read a manometer. Essentially what it is a glass tube where liquid mercury is pretty much sandwiched between a gas and the pressure of the atmosphere, so the air. So on one side of the tube we have the gas, then we put the liquid mercury inside the tube, and then the remaining air in the tube comes from the atmosphere. So typically it's open-ended. If it's closed-ended, we'll talk about that in a minute. But basically what we have here is one side is your atmosphere, the other side is your gas, and in between is some amount of mercury that's in our tube. Now when we're looking at the balance between the level of mercury, we've got 2 different situations we can consider. We have a situation where the pressure of the gas is less than that of the atmosphere, in which case the atmosphere appears to take up more space in the tube. When that's the case, the mercury will be higher up on the left side, and we would use this equation here. The pressure of the gas is equal to the atmospheric pressure minus the height. When we have the converse, when we have less atmospheric pressure and the pressure of the gas is higher than that of the atmosphere, the height in the tube will be less on the left side. It will actually be higher on the right side. In that situation, we would add the height to our atmospheric pressure. Now, in a closed-end manometer, the height is equal to the gas pressure. So, in this last situation, that is our our height, and that is our pressure in centimeters, so we'll have to figure out how to get that to millimeters or something useful. Okay, so the atmospheric pressure in all of these situations is 0.975 atmospheres. We want to know what the pressure of the enclosed gas is in each of the 3 cases. So I want to first figure out useful numbers here because they give me centimeters and millimeters, and that's going to get tricky. So 520 centimeters is the same as, 52 centimeters is the same as 520 millimeters. I think that's going to be useful for me in terms of my calculations. I then can take that and convert that to a pressure in atmospheres, right? So 520 divided by 760 millimeters of mercury gives me a pressure of 0.684 atmospheres. All right, and now this is a situation, like I said, this is going to use the first equation. I know that my pressure of my gas is less than that of the atmosphere, so I have to do the pressure of the atmosphere minus my H. Here's my H. My pressure of the atmosphere is 0.975 atmospheres, and if I subtract the two, I should be able to get my pressure. So 0.975 minus 0.684, and I get 0.29 atmospheres, or 291. Okay, 29 because there's only 2 sig figs. Go ahead and calculate the pressure for situation number 2. Be mindful that the height is higher on this side, meaning we're going to be using this equation. Okay, you should have gotten 1.063 atmospheres. The pressure of the gas is higher than that of the atmosphere, so we expect it should be larger than 0.975, so we add them together. All right, and then the last one, we know that it's closed, so the height here is equal to the gas pressure, so this is really 103 millimeters of mercury, which we can just convert. And by converting that to atmospheres, we should get our answer of 0.136. Okay. All right. This one is a Charles law problem. So Charles law, we see that our volume is 2.58, and we're told that the pressure stays the same. That's good, but we change our temperature and we want to know the new volume. So V1 over T1 equals V2 over T2. Again, anytime temperature is involved, we got to convert Kelvin or temperatures to Kelvin. So 15 degrees Celsius plus 273, that gives us 288 K. And then T2, we've got 38 degrees Celsius plus 273, just 311 Kelvin. Okay, so let's plug in. We've got, what do we got? What's our volume? 2.58. We got 2.58 liters over 288 Kelvin, and we've got our new volume, which we're looking for, over 311 Kelvin. All right, so my trick to solving here, cross multiply. Every time with these direct relationships, just cross multiply. We've got 2.58 times 311 and divide it by 288, and we get our volume V2. We get our volume V2 equals 2.79 liters, okay? Which makes sense, our temperature increased, therefore our volume goes up. This is a good one. We are given a volume and an amount of moles. This is actually going to be our Avogadro's law or the Amonton's law, even though it wasn't on the 4 that I showed you earlier. I am given moles, and I am asked to find the volume of ozone. Now this one is tricky because it's actually a little bit of a stoichiometry problem. There's a couple of things we know. Let's label. We've got our initial volume, and we have our moles, N1, of O2, right? We've got our moles of O2. Tricky part is we don't know our new volume. That's what we're going to calculate for. And we also don't know our moles of ozone. So we need to figure out the moles of ozone. We're going to need a balanced equation here. Okay, so we know oxygen gas is converted to O3. If you balance, we get this ratio of 2 to 3. This is where the stoich comes in. We're going to need to find our moles of O3 before we can use this equation here. So moles of O2, use your coefficients as a mole ratio. We've got 3 moles of O2 for every 2 moles of O3. And if we convert 0.5 times 2 divided by 3 on the bottom, we get 0.33 moles of ozone. All right, so now we know that this is 0.3 moles. So then we can plug and chug just like the Charles Law problem. And since the amount of moles went down, as you can expect, we probably are going to have a decrease in our volume. I'm actually just going to put the answer times the answer. Good. So that, and then divided by 0.5. And I get a volume of 8.1 liters. Just checking my key. Yep, 8.1 liters. So combined gas law, P1V1 over T1 equals P2V2 over T2. All right, so we don't need to change anything here except our temperatures. I know that V1 is 5.05 liters. I know that P1 is 650 torr. I know that T1 is going to be 25 degrees plus 273. That's my 298 K. If I go through and label the other ones, V2, this is what I'm looking for. P2 is raised by 35 torr. Got to read carefully here. So we're raising by 35 torr. We've got 650 plus 35, looking at 685 torr. And then my new temperature is also raised by 34 degrees. So 34 plus 25, that means 59 degrees Celsius plus 273, looking at 332 Kelvin. Or if you just wanted to add 34 to your 298, you could have done that too. All right, same deal, we're going to plug everything in, and once we plug everything in, so I've got 650 times 5.05 times the bottom of my second one, so 332, and then I'm going to divide that by 298 times 685, right? Cross multiply. And that gives me a V2 of 5.34 liters. Okay. And that is all for today.